and welcome to the course on power electronics. This lecture is on control rectifiers and specifically on the single phase full converter. Now, the single phase full converter is a bridge configuration which looks like this. Now, we have 4 thyristors which are connected in the form of a bridge, and a full converter has 4 SCRs which are connected in the form of a bridge. Now we saw the single phase semi converter which has 2 thyristors and 2 diodes. Semi converter is a half control converter, whereas a full converter is a fully controlled converter. Now what do you mean by this? Fully controlled AC to DC conversion or rectification is done. That is the purpose of a full converter. So in a bridge rectifier, normal conventional bridge rectifiers use diodes, whereas the semi-converter uses 2 thyristors and 2 diodes, and the full converter is using 4 SCRs, right? So at any time you have 2 diagonal elements conducting. So 2 diagonal elements in the bridge will be conducting. So in this case, T1 and T2 will be fired together and they will conduct together. Similarly, T3 and T4 will be fired together. So this is how the conduction is going to be. So the purpose of this is that you convert the input which is given from this supply, AC supply. So the AC is converted to DC at the output. So this is the purpose of the full converter. So we have the single phase full converter. So the single phase full converter is a bridge configuration, and the thyristors T1 and T2 are going to be forward biased during the positive half cycle. So they will conduct during the positive half cycle provided they are given gate pulses. Similarly, T3 and T4 are forward biased during the negative half cycle, and you have to give pulses to both T3 and T4 together so that they'll conduct together to give a voltage across the load. So 3 things which we have to remember here is that the thyristors T1 and T2 are fired together at some alpha. So during the positive half cycle, T1, so positive half cycle is like this. T1 and T2 are given pulses. So first let me draw the waveform. So this is the supply voltage and pulses are given, the gating pulses are given to Ig1, G2. So the pulses for T1 and T2 are the same pulse, firing pulse. This is at some alpha. So very small alpha here I've considered. So alpha can be varied. And again at pi plus alpha, so at some pi plus alpha, we are going to be firing the pulses, the thyristors T3 and T4. So what is the voltage across the load? Now, when we have T1 and T2 fired together, so when T1 and T2 are on, the load voltage is going to be equal to VLN. This is what we had seen before also during the semi-converter. When T3 and T4 are on, output voltage is going to be equal to VNL. Why is this so? Is because T1, you can see from the configuration, from the connection, that the thyristors, the T1 is connected to L terminal, T2 is connected to the N terminal. So when T1 and T2 are connected together, the current is going to flow like this through L, T1, then through the load T2 and back. So at the load terminals, what is the voltage which is coming across the load terminals? This point, so let me name this as say AB, the load terminals A and B. So when the current path is like this through T1 through the load, so this load terminal A is connected to the positive terminal of the supply and B is connected through T2 to the negative terminal of the battery. So effectively the load voltage VO or VAB is nothing but VLN. So during the positive half cycle, L is positive with respect to N, so which means we have an output which is positive across the loop. Now, during the negative half cycle, it is going to be N is positive with respect to L, so it is going to be the reverse. So here, instead of L and N positive, L positive, you have N which is positive. So now the current is going to be flowing from N through the T through the load, and then through T4 and then back to the supply. So the load terminal, so A point is again connected through T3 to N, but N is now positive. So at the load terminals, we are again getting a positive output voltage. So your output voltage looks like this. At alpha, till alpha, the thyristors are not gated, so there's no output voltage. And at alpha, when you're firing the thyristors, this much part of your waveform, this part of the waveform is what is coming across the load, because your load voltage is nothing but the supply voltage, and the supply voltage at that instant is this much. So from alpha to pi, you have got the voltage which is equal to VLN across the load, and from pi plus alpha, so this is your pi plus alpha to 2 pi. So this is 2 pi you have got. So this is for T1 and T2 conducting, and this is for T3 and T4 conducting. So from pi to pi plus alpha, again, there are no devices which are conducting. Why? Because T1 and T2 are fired during the positive half cycle only. They turn off at this instant. Now, in instant pi, what is happening? Voltage has become zero. Since you have got a resistive load, the current also becomes zero. For a resistive load, the voltage and current are in phase. So the current also becomes zero at this instant. So thyristors T1 and T2 will turn off by natural or line commutation, we call it as. Now from pi to pi plus alpha, we have not at pi plus we have not fired the thyristors T3 and T4. So T3 and T4 are also fired only at pi plus alpha. So they are also not conducting. So between pi and pi plus alpha, no device is conducting. So your output voltage is zero across the load. So when we are firing T3 and T4 together, again the load voltage becomes positive, like we said before, and we've got output. So this continues, and we can see this is the case for a single phase full converter with resistive load. And if you observe this, it is seen that it is very similar to that of the single phase. It is the similar waveform as that of a single phase semi converter. So this is how the waveforms are going to be. So the shaded part is the load voltage which is happening, and like I said, here the voltage. So two waveforms, which is the one which is shown in dotted is VNL. So if I call this as VLN, the VNL is positive. So this one is negative with respect to VLN, and this is your VNL. So during the negative half cycle, this the L terminal is negative, but the N terminal is positive. So that is why across the load terminal, we are still getting positive because of the connection as such. So T1 and T2, so as we said, T1, T2 is conducting, T3, T4 is conducting during this cycle. So this is pi plus alpha, this is alpha, and this is 0, and this is 2 pi. So if you find out the average voltage, this is very similar. The waveform is just looks like the that of the semi-converter. So when you're finding out the average voltage, you are integrating over the whole period. Period is pi. So from 0 to alpha, there is no output, right? So from 0 to alpha, there's no output. Only from alpha to pi, there is an output. And the period, the whole waveform is repeating after a cycle of pi. So your period is pi, and the limits will be from alpha to pi, since you do not have any output from 0 to alpha. So alpha to pi of Vm sine theta d theta. So we had already seen this. This one is the expression, same expression as that of your semi-converter. So the full converter with resistive load has got the same output expression as that of the semi-converter. So, so effectively, so if you have a resistive load, then it's better to go for semi-converter. Why? Because we need to control only two thyristors, right? Semi-converter is only preferred because we get the same expression. The output expression is exactly the same, and the waveform, the waveform is the same nature as that of the semi-converter. So in that case, semi-converter requires only two SCRs. We need to control only two SCRs, whereas here you need to full converter, you require four to control four SCRs. So the design is more complicated in that case. So if it's a resistive load, then semi-converter is preferred. So the difference comes when it is an inductive load. So let's see this. So now this is a single phase full converter with inductive load. Now what is going to be different? First thing, T1 and T2 have to be fired together during the positive half cycle. T3 and T4 are fired simultaneously during the negative half cycle. This remains the same, but your load is now an inductive load. So what is different here? The conduction during from at pi is slightly different here. So that is because of the nature of your inductor. Now we know that inductor is a component through which current cannot change instantaneously. So inductor current cannot change instantaneously. What do you mean by this, or what is the significance of this? Like in the case of your uh, resistive load, where when voltage was becoming zero, the current immediately was becoming zero, and hence the thyristors turned off. But now here, when the current is flowing through an inductor, it cannot suddenly become zero. So what has done, this current only slowly becomes zero. That is a property of an inductor. So instantaneous changes of currents are not possible through the inductor. So what will it do? It opposes this change, any change, by inducing an opposite polarity voltage. This is basic inductor basics, opposite polarity voltage. So what is going to happen is, when T1 and T2 are conducting together, your output voltage that we have seen, that is equal to your supply voltage, or VLN. Now during the positive half cycle, when during at your yes at pi, during the positive half cycle, T1 and T2 are fired together at some alpha, so they will conduct together but at a time pi, at angle pi, what is going to happen is that voltage has become zero, and now it is reverse bias. The supply voltage has gone into reverse bias. Now what happens is that the current was flowing through the thyristor in this direction, from L through T1, through A, B, and through T2 and back. This was how it was. Now it is in the negative half cycle, and the voltage has reversed. But the current through the inductor cannot immediately reverse. So this is what we said. Inductor current cannot instantaneously become negative. So it has to it has to slowly only decrease to zero. So what happens? The current will be flowing the same direction. It cannot instantaneously change its direction also. So the current will flow in the same direction. Now how can it flow? There is no other path for it other than the thyristors T1 and T2. So what does the inductor do? It induces an opposite polarity here. So to oppose the change. So what we are speaking about is, we have reached the negative half cycle at pi. The voltage is reversed. The current through the inductor cannot immediately reverse. So the current will continue to flow through the thyristors T1 and T2 only. Now, how is that possible? Because T1 and T2 are now reverse biased actually by the supply. So to maintain the current in the same direction, the inductor induces an opposite polarity voltage like this. Now what happens is that we can see that thyristor T1 cathode is at negative, this T2 anode is at positive voltage, and the inductor maintains the thyristors T1 and T2 in the forward bias direction only. So the current is going to be flowing through in the same direction only, right? So the current is flowing through thyristors T1, through the load, through T2, and then back like before. So it is uh, the load has induced an opposite polarity voltage, which is actually maintaining the thyristors T1 and T2 still in conduction. And we know that when thyristors T1 and T2 are conducting, your output voltage is equal to VLN. And what is VLN now? It has become negative. So, which means that you're going to be getting some part of the supply voltage, which is negative across the load. So, which means that your load voltage now is going to be negative. So, from here, from alpha to pi, the thyristors were conducting. So, I'm assuming that at alpha, T1 and T2 are given pulses. T1 and T2 are fired together, and they are conducting from alpha to pi, and they continue to conduct from pi to pi plus alpha till you are going to be firing the thyristors T3 and T4. So T3 and T4 are going to be fired at some pi plus alpha only. So till that time, we are assuming that T1 and T2 are conducting. Now, for this to be practically possible, the inductance must be large. The value of inductance should be high. So we are considering the case where if it is not high, so what is happening is inductor is a component which stores energy. So the inductor stores energy during the positive half cycle when T1 and T2 are conducting, and the inductance when in the negative half cycle from pi to pi plus alpha, what is the inductor doing? The whatever energy it has stored, it is actually returning back to the supply. You can see that the load is now returning whatever energy it had stored back to the supply terminals. This is where the current is now. In this case, the voltage is negative. Why? Because if you see, the load has reversed its polarity, right? And the load voltage, like I said, when T1 and T2 conducting together, VO is equal to VLN. VLN is now negative. So your supply voltage is negative at this term. So that is what is appearing across the load terminals. But what about the load current? The current is still positive. So load voltage is negative and load current is positive. So this is what happens for the full converter with RL load. Now what is going to happen at pi plus alpha when we are firing the thyristors T3 and T4 at that time? Then, so during the negative half cycle, so this we are still in the negative half cycle. So when T3 and T4 are fired together, what will happen? At that time, they will start conducting, and then thyristor T1 and T2 are turned off naturally. So when thyristors T3 and T4 come on, we'll say that T1 and T2 get reversed as they are turning off due to line commutation or natural commutation only. And the current is now starting to flow again, like in from pi plus alpha, it is going to the same cycle. So now the current is going to flow from N through T3 through the load, then to T4 and back to the supply, back to L. So now still we can see that the load current is always positive only, right? So the load current, so in this case, when T3 and T4 were conducting, so N, then T3, then load, then your T4, and then back to L. Load current is still from A to B. So what is happening now? When T3 and T4 are conducting, at that time, what was the voltage? Like we saw before, T3 and T4 on, load voltage is equal to VNL. Now, when VLN is positive, your VNL is negative, and when VLN, this L is negative with respect to when L is negative with respect to N, you have VNL which is positive. So when your T3 and T4 are conducting, VNL is positive, and we have got this voltage, and this is going to continue. And again at pi, the same thing happens. The load is going to, so the current cannot instantaneously reverse because we have reached again a zero crossing, and the current cannot become immediately zero, so it will continue to flow through T3 and T4 combination. So what is basically happening here is that every time we can see that the load current is positive, right? But we have got some part of the supply of the load voltage is negative also. This is how the full converter with inductive load works. So again coming back to the waveforms. So this is how the waveforms are going to be looking like. So now this we are considering the case for continuous conduction. Now what do you mean by continuous conduction is that we are assuming that the load is a very large. So the inductance L is very large. If inductance is large, then the load stores energy, and since it's a very large inductive, highly inductive load, then what happens is that during the whenever T1 or T2 or T3, when T1, T2 or T3 and T4, one of these combinations are conducting, at that time the load is storing energy. So the load stores energy during the times that T1, T2 conducts, or when T3, T4 conducts. During the time that this is become, so if you observe the waveforms here, so let us observe it from here. At alpha, we are going to be, so at, sorry, this is alpha. At alpha, T1 and T2 are fired together. At pi plus alpha, T3 and T4 are fired together. So at that time, so when T1 and T2 are fired, so your load voltage is positive. From here to here, you have the voltage. And then at pi, the voltage is becoming negative. Why? Because like we said, the inductor, whatever energy it has stored, it is now returning to the source through the combination of T1 and T2. The load current, like we said before, the load current was flowing like this from A to B. At pi, supply voltage has become zero and it is negative. So the supply terminal has become reverse bias, but the current through the thyristors T1 and T2 will continue through the load terminals. So as long as that, so the T1 and T2 are carrying the same current as the load current. Since the load current cannot become zero immediately, and it will continue in the same direction through the same path through thyristors T1 and T2 only. So when that is happening, since your line voltage is now negative, this is what your load voltage is going to be. So for some time from pi to pi plus alpha, your load voltage is going to be negative. So at pi plus alpha, from pi to pi, what is happening at pi plus alpha? We are going to be firing the thyristors T3 and T4 are fired together. So when T3 and T4 are fired, they will turn off T1 and T2, and again the same thing happens. So this is now negative and positive. So we were speaking about the at pi, when the line voltage has reverse, actually the current was flowing through the load terminals like this. It cannot become zero immediately, so that is why the current was flowing like this, and it continued through T1 and T2. As long as there is current through T1 and T2, so they're going to be conducting. Now to maintain that, the load has induced an opposite polarity here, which maintains T1 and T2 again forward biased. So this is what happens, and you can see that a part of the load is now negative. But if you see, this is for small values of alpha. So alpha, when it is small, average voltage is positive. If you see, because you have a more positive voltage than the negative period. So the negative interval is small than the positive. So we can say that this interval, this is alpha and this is pi. So the pi minus alpha, so pi minus alpha is greater than the alpha period. So in this case, so suppose consider alpha is equal to some 30 degree or so. So which means, let's say, right, so pi minus alpha is what, 180 minus 30, which is 150. So that is quite a large period, greater than 30 degrees. So which means what, for this period your voltage is positive than the period for which the voltage is negative. So your average voltage is going to be positive. So alpha, so it is seen that for alpha lesser than 90 degree, your average voltage is positive. So let us try to derive the expression for alpha. So average voltage VC. So it is something, your waveform, I'm just trying to, this will be alpha, this is pi, pi plus alpha, and 2 pi and so on. So when we are finding out the expression for average output voltage, again you can see this is repeating after pi. So average voltage, you integrate over the whole period. Period is, so the formula for the average voltage is 1 by t integral of 0 to t of your v omega t d omega t. So this is your expression for the uh, uh, average voltage. So since your period is equal to pi in terms of pi, so 1 by pi integral 0 to, the interval limits are going to be from alpha to pi plus alpha. Have the expression is Vm sine theta d theta, right? So Vm sine 1 by pi from alpha to pi plus alpha, your wave is repeating, and this is a sinusoidal wave. So Vm sine theta d theta, again that is going to repeat. So if you do this, when you put the limits, we are getting the expression 2 Vm by pi into cos alpha. This is the average voltage of a full converter with an inductive load. So 2 Vm by pi cos alpha. And similarly, RMS voltage, V output RMS value is root of the mean. Mean is pi, or period is pi, from alpha to pi plus alpha of Vm sine theta the whole square, or Vm squared sine square theta d theta. So RMS is root of mean of the squares. So mean of this is the square, Vm square sine square theta. We get this act is equal to Vm by root 2. So the RMS value for a full converter is Vm by root 2, similar to that of a sinusoidal wave, and the average output voltage is given by 2 Vm by pi cos alpha. So when we observe the DC or average value, we see that it is 2 Vm by pi into cos alpha. Now what do we observe from this? For alpha lesser than 90 degree, your output voltage is going to be, so this is what we already spoke about, VDC is going to be positive, or average voltage is going to be positive, right? So if you see alpha is equal to 0, so when alpha is equal to 0, your output voltage, average voltage, is going to be equal to 2 Vm by pi. When alpha is 90 degree, your VDC is going to be equal to 0, cos 90 is 0. And if alpha greater than 90 degree, then we can see that this is negative. So for alpha lesser than 90 degree, now again coming back to the wave, this, if we again see the waveform for alpha something lesser than 90 degree, this is how it is going to be looking like. Just drawing it roughly, alpha, pi, pi plus alpha, and so on. Now what do we see? From alpha to pi, your output voltage is positive. Then from pi to pi plus alpha, your output voltage is negative, right? So from alpha to pi, your VO is positive and IO is positive. Output current is always positive, right? The current through the load is always in the same direction from A to B. So output current is positive. So we can say that the power is positive. Now from pi plus alpha to, sorry, from pi to pi plus alpha, this point, from pi to pi plus alpha, if you're seeing, you can see that the voltage is negative, right? So from this period to this period, your voltage is negative. So average voltage is negative, but your current is still positive. So which means that, so IO is, VO is negative, IO is still positive, which means the power is negative. Now, power positive means power flow is from source side to load, source to load. And power negative means from load to source. Now, when alpha is lesser than 90 degree, we can see that, so this period alpha to pi, this point is actually from alpha to pi. When alpha is small, this period is more, the positive period is more than the negative period. So average voltage is going to be positive. So our average flow of power is going to be from the source side to the load side. Now what is your source? Source is the AC. So source side is AC, load side is going to basically you want the DC side. So this is the DC side. So when the power flows from the source to the load, we say that from AC, it is from the AC side to the DC side, or we are getting average output DC. So that is called as rectifying mode. When you have AC to DC, net power flow is from AC side to the DC side, or net, we can say that AC to DC conversion is happening, or it is in the rectifying mode. So this happens for alpha lesser than 90 degree. So for a full converter, for alpha lesser than 90 degree, average voltage, from the formula also we can understand, the average voltage is positive in nature. And from the waveform also you can see that more positive than the negative period. So because of it, average voltage is going to be positive. So you can see here, like we said, from alpha to pi, voltage is positive, current is positive. So net flow is, we can say, from the AC to DC. Now what is happening during pi to pi plus alpha period? From the pi, at the pi to pi plus alpha period, the load is returning whatever energy back to the source. So that is from DC to AC. But since your alpha is small period, so effectively average, on an average, the net power flow is from the AC side to the DC side, or from the source side to the load side. So that is, since it is AC, source side is AC, we say that AC to DC is a rectification. So this is called as a rectifying mode of the full converter. So for alpha is equal to 60 degree, these will be the waveforms of the full converter. So if you see here, so this waveform we have already seen, these are the pulses. Now what do you mean by this? This is the load current. It is seen to be constant. Now I already said we are considering the case for inductive load, which is very highly inductive. So these are the case for highly inductive load, or in other words, it is also called as continuous conduction. So when we are speaking about continuous conduction, means that the load is very highly inductive. Actually, the load current is something of this nature. It stores energy, so the current increases. And when it is returning the energy back, so the current will be decreasing. But before it decreases fully, the next cycle has started, and then it starts increasing again. So if you see, the average value is positive only. So we are considering the load current to be constant like this, even though it is exactly not the same. But this as as an assumption which we can take, which means that your load is very highly inductive. So effectively, we are seeing a constant line which shows continuous conduction. Now, some of the waveforms which we draw here. So to remember all this, how to draw the waveforms. Now we are safely, so to make our analysis simpler, we have considered the load line. So IL is constant, this is what, and continuous. Obviously, it is continuous, means it's constant. There is always current through the load, and we are assuming it to be approximately constant. So this is your average load current which we are drawing. Now, when we are drawing the thyristor current, suppose, to how to draw the waveforms for thyristor currents. So if I want to draw the currents for T1 and T2, now T1 and T2, they are carrying, so when they are conducting, they are carrying the load current only. So whenever they are conducting, they are carrying the load current. And when they are not carrying, when they are on, they are carrying the load current. And when they are off, obviously the current is equal to 0. So if you want to draw the waveform, so when during from alpha, from alpha to pi plus alpha, your thyristors T1 and T2 are conducting. Like here, if you see here, the thyristors T1 and T2 are conducting during the speeds alpha to pi plus alpha, they are conducting, right? So from alpha to pi plus alpha, T1 and T2 are conducting, and the current, what is the current through them? They are just carrying the load current. So the current through the T1 and T2 has to be shown as the load current only. So what is the value of the current? It is nothing but the load current IL. So load current we have already shown, this is the constant, and the value of this is going to be equal to that of your load current IDC. So this value will be IDC or IL. I've just shown it as IL or IDC. So this is the load current. When this is alpha to pi plus alpha. Now pi plus alpha, what is happening? T3 and T4 conducting. So pi plus alpha to again the next. So this is your these instance. This is alpha, this is pi plus alpha. Then they are again going to conduct only at 2 pi plus alpha. So till 2 pi plus alpha, they are off and then it repeats. So this is how you are going to be showing the current through the thyristors. So T1 and T2 are going to be conducting during the positive halves, from the intervals alpha to pi plus alpha. So when they are conducting, their current is equal to the load current. When they are off, the current is equal to 0. So it's very easy to draw. Similarly, when you are drawing the voltage across the thyristors, how do you draw the voltage across the thyristor waveforms for that? So V T1 or T2, if you are to draw. So when they are on, what will be the voltage? Because we are assuming that they are ideal devices, so voltage is equal to 0, we can assume. And when they are off, their voltage will be equal to the supply voltage, right? So Vt is equal to Vt is the how we represent the thyristor on state voltage. So when they are on, the voltage is equal to 0. When they are off, that is equal to the supply voltage. And supply voltage or basically VLN, or what we can see, this is your VLN which we have shown, right? So this voltage is T1 and T2 are connected across the terminals LN. So that will be the same voltage which is happening across thyristors T1 and T2. So see here, 0 to alpha. 0 to alpha period. The thyristors T1 and T2 are triggered at alpha only. So from 0 to alpha they are off. So if they are off, then the voltage is equal to the supply voltage of VLN. What is VLN at this period? So it is this much part. So this much part of the supply will come. So when they are off, they have to withstand the supply voltage. When they are on, their voltage is equal to 0. So from alpha to pi plus alpha, they are on. So the voltage is equal to 0. Right? Because why do we consider the voltage is equal to 0? We are considering them to be ideal devices. So it's like a short circuit. So when it is like a short, the voltage across that short is equal to 0. That is why this is. So actually there will be an there will be a practical voltage of around some 1 volt or whatever the device is. Thyristor practical voltage drop will be there. But now we are assuming them to be ideal devices. So from alpha to pi plus alpha, since these devices are on. So I'm showing these devices T1, T2 are on here, right? So when T1, T2 are on, alpha to pi plus alpha, what is the voltage drop across them? That is equal to 0. And at pi plus alpha, T3 and T4 are fired. What will be the voltage across them? They are off. Supply voltage will come. What is the supply at that time? That supply voltage is negative, right? So till here they were conducting and now the supply voltage is negative. Do not get confused with this. So this is VLN and this is VNL. So your thyristor voltage when T1 and T2 are connected across the terminals L and N, so their voltage will be whatever the condition of VLN will be, that will be followed. So you can see this is your VLN and that is negative. So from here to here, whatever VLN is, that is coming across. So this is your just following what is VLN. And VLN has become positive here because the positive half cycle has again started. So now the still here till the thyristors again fired, right? So when they are fired, again the voltage becomes 0 and so on. So this is how you draw the waveforms across the thyristors. So always keep in mind when you're drawing the voltage across a device, when it is on, the voltage will be equal to 0. When it is off, it has to withstand the supply voltage. Any device, this is true for any electronic device. When the device is on, the voltage will be equal to 0. So keeping this in mind, we can draw the waveforms. And this is for the supply current. So this we'll see again later. The supply current waveforms are going to be, we'll draw this in the next slide. To draw the supply waveforms, supply current waveform. So how do you understand this? Again, you have the thyristors T1. So this is T1, T2, T3 and T4, and these are the line terminals L and N, and this is your inductive load. And so we are again considering the case of the inductive load. So the supply current waveform, this is what we are going to draw now. Waveform. So we already saw that when T1 and T2, so how is the supply, how do we draw the supply current? When T1 and T2 are conducting, supply current flows from, because when T1 and T2, T1 is connected to L and T2 is connected to N. So the current is going to be flowing like this, conducting. Supply current is equal to load current, that is there, and IS flows from L to N. So we can consider that to be positive. Now when T3 and T4 are conducting, it is from N to L, right? So the supply current, so when the supply current can be said, so this is L to N, we consider this to be positive. Is magnitude is equal to IL, but Is is magnitude. This is the magnitude of the current is the same as that of the load current, but Is is negative. Why? Because it is starting from N through T3 through the load through T4 and back. Through the load terminals, the current is still positive only from A to B, but through the supply terminals, it is from N to L. So if I draw the current waveform, so from alpha, we'll start from alpha. So from alpha to pi plus alpha, if I draw it, the current magnitude is equal to the load current, which is constant. But at pi plus alpha, the current direction goes from N to L. Now the supply current direction changes from N to L. So because of which the current, still the magnitude is the same, because the current is going to flow. So from whether it is from L to N or N to L, the current is, when it is from N to L, how is the current going to flow? It is going to be like this, from N through T3, then through the load through T4 and back to L. So the current through the supply terminals is from N to L now. So that is why we call it as negative. So this is your negative supply current when T3 and T4 are conducting. So this is how you draw the waveform for the supply current. So the supply current being uh, this is 2 pi plus alpha, right? So this is when T1 and T2 are conducting. This is when T3 and T4 are conducting. So keep this in mind, and how the supply current flows. So in this case, there is no freewheeling as such. So we saw the condition for freewheeling in semi-converter when the current through the load is just circulating through the devices. So in semi-converter, it was a thyristor and a diode combination, and the current used to circulate through that during the period from pi to pi plus alpha and so on. But that does not happen in the full converter. And in the full converter, the same current is just flowing through the supply terminals also. So when T1 and T2 are conducting, the supply current is there. When T3 and T4 are conducting, the supply current is negative. So this is how the supply current is drawn. Now the inverting mode, this was when the condition. Now we will again write the expression for your uh, the wave average voltage. So average voltage, we already saw the average voltage wave expression is given by PDC is equal to 2 Vm by pi cos alpha. So for alpha greater than 90 degree, what is the value of VDC? VDC is going to be negative, right? So we can see this. So during, again, alpha is greater than 90 degree means more than 90 degree values. So which means that only a small value of the voltage waveform is going to be. So it is something like this. Suppose alpha, this is your supply voltage waveform. So alpha is greater than 90 degrees, so somewhere over here. So this much part will be there, which is positive, and then we are going to be having a large negative value, and then again this is going to be positive, and so on, right? So the negative part is going to be actually more than the positive part. This is how it is going to be looking like. So average voltage is negative. So we can say average voltage is negative, or in other words, if you see in this case, from 0 to alpha, this is pi plus alpha, this is 2 pi, and so on, right? So from 0 to alpha, your voltage is negative and your current is positive still. So what we can say is voltage, so average value in this case is negative, more towards the negative side. So net power flow, if you see, power is equal to V into I. Voltage is, average voltage is negative, current is still positive. So your power is negative. Power negative means average flow of power is from the load side to the source side. The load side is DC, right? So from the DC side of the converter to the AC side of the converter. So now conversion of DC to AC, or movement from DC to AC, is considered as an inverter. So AC to DC is a rectifier. We call DC to AC operation as inversion. So we can say that this is called as a line commutator inverter. Line commutation means the devices turn off naturally without any other external circuitry. So when do these devices turn off? When suppose T1 and T2 were conducting, T3 and T4, when they are turned on, T1 and T2 automatically turns off. So that is called as line commutation. So this process is called as the inverting mode of operation of the full converter. Now this has applications in something called as regenerative braking. Now regenerative braking is normally used in, like, for example, electric vehicles, etc., to assess the braking. Normally, braking is a process which has got lots of wastage of power with it when you press the brakes, manual brakes. So regenerative braking is where basically by making the power negative. So since the voltage is negative and the current is positive, your average power is negative, or this is used to brake or reduce the torque and brake the vehicles. So this is what happens in regenerative braking. This will be discussed later on in DC to DC converters also, process of regenerative braking. So this is just the how the full converter can be working can work as a rectifier as well as an inverter. So this is for the waveforms of with alpha is equal to 135 degrees. So similar to the case of rectification in waveforms, the way in which the waveforms are drawn are similar, but we can see that here alpha is greater than 90 degrees, so your negative portion is much more than the positive portion. So that is why we are saying average voltage is going to be negative in this case. Average voltage is going to be negative, so which means that your full converter is a two-quadrant converter. Uh, Full converter is a two-quadrant converter. What does that mean? It can work like this. It can give both average positive voltage and negative voltage, but your load current is going to be always positive. So if you just make a, this is where your load voltage is positive and load current is positive. That is, this is a rectification mode, and when voltage is negative, so and the current is positive, this is the what do you say, inversion mode. So the full converter can work in both the modes depending upon what we require. So seeing the waveforms again, so you can see here the currents waveforms for T1 and T2. Again, T1 and T2. So when drawing these waveforms, always mark the instance of conduction of the devices. So here at alpha, T1 and T2 have been fired. You can see the pulses. Only thing, this alpha has become larger now at 135 degrees. So the pulses have been given to T1 and T2. From here to here, they are conducting. So T1 and T2 are continuing to conduct from here to here. Then after that, it is T3 and T4. You can see the pulses which are given, right? And then again, So T3, so firing pulses, this is for T1 and T2. In the same diagram, it is shown actually the pulses are going to be like the whichever thyristor is forward biased during the corresponding cycle is going to conduct. So T1 and T2 will conduct, then you have T3 and T4 which is conducting, right? So when T1 and T2 are conducting, what is the current through that? The current is going to be equal to the load current. That is why, and again I'm assuming continuous current through the load. So the load current is continuous, constant. So this is not shown here. The load current is some value which is constant, right? So this is your load current, and when the thyristors are conducting, the current is going to be equal to the load current. So that is what is shown over here. From here to here, thyristors T1 and T2 conducting together, the current magnitude is equal to the load current. From here to here, T3 and T4 conducting, T1, T2 are off, so current is 0. Now, what about T3 and T4? So T3 and T4 are conducting during this period, then they are off during this period, then again turned on, and so on, right? So at pi plus alpha, so just see the instance of conduction also, or mark the instance of conduction. So this is alpha, this is pi plus alpha, and so on. This is alpha, this is pi plus alpha, this is 0, this is 2 pi plus alpha. So this is pi plus alpha, right? This is 2 pi. And since the alpha itself is very big, that is why such a large gap, 2 pi plus alpha and so on. So you can see that whatever it is, alpha values is, the conduction period of the thyristors T1 and T2 will be equal to from alpha to pi plus alpha, which means they conduct for a whole period, half cycle, right? So alpha to pi plus alpha. So the period is pi of conduction. Not period of conduction. The time or duration of the conduction is for a whole half cycle they are conducting. For a duration of pi they are conducting. For a period of pi they are off. So 2 pi plus alpha to pi plus alpha they are off, which means total duration of pi they are off. So each thyristor pair conducts for 180 degree in this case. Now the voltage also, like we saw for the other case, when these thyristors are on, so T1 and T2 are turned on from here. From here to here, their voltage should be equal to 0, right? So they are on. And when they are off, they have to withstand the supply voltage. Supply voltage is positive from here to here. So that is what is shown. And then they are turned on. So once they are turned on, they will be the voltage will be 0. Then when they are again turned off, they will have the supply voltage across. So supply voltage is now negative. So that much supply voltage will be coming across them. And then again till the time they are fired, again the supply voltage is going to be there. So this is how you draw the waveform of the voltage across the thyristors, right? And this is for the supply current. So supply current, again, like I told before, the supply current is going to be, so from alpha to pi plus alpha, your supply current is going to flow through the thyristors T1 and T2 from L to N, right? This is the supply current. Supply current is flowing from L to N is positive. From N to L, when T3 and T4 are conducting, so that is shown as negative. So when the current flows from the terminal L to N, it is positive. When it flows from N to L, it is negative. So during the instance that T1 and T2 are conducting, so T1 and T2 are conducting from alpha to pi plus alpha, so the supply current is positive. And then it becomes negative, the magnitude being equal to the load current, right? So this magnitude, this value is equal to the load current, because whenever the current is flowing, the supply current is flowing through the load terminals. This is what. And what is shown over here, the supply voltage is also shown. The supply voltage and the supply current are shown. So you can see, so the supply current is a square kind of waveform. So it has got a fundamental component. So this is the basis for expressing the supply current in the form of a Fourier series. So we'll see that, discuss that next in the next session. The supply current is not properly sinusoidal. We can see the supply voltage is a sinusoidal waveform, but the supply current is not a sinusoidal waveform. So it will have harmonics, which will actually affect the performance of the of the circuit. So we'll have to analyze that to find out the harmonic component of the waveform, etc. Okay, so this we'll see in the next class. So this will be the waveform. So the actual supply current waveform is kind of a square waveform like this, square or rectangular waveform we can see. So this is for the full converter with RLO. Okay, to summarize, we have discussed the full wave converter with resistive and inductive loads. Seen all the waveforms which are related to the waveforms like average output voltage, then the load current, then the supply current waveforms, then how to draw the voltage across the thyristors and the currents through the thyristors. These waveforms have been seen, and for different values of alpha, derivation of average and RMS output voltage, and how it affected the rectification and inversion modes. So we saw that for alpha lesser than 90 degree, it is rectification mode, and for alpha greater than 90 degree, it's an inversion mode. So this have been discussed. Thank you.